Hi, welcome back. In our previous lesson, we started with the algebraic approach of solving the consumer's problem. Today, we'll be moving on to the Lagrange method. So the equilibrium bundle is the bundle that maximizes the value of the individual's utility function. Now, a typical example of a consumer's problem is to maximize their utility subject to their budget constraint. And this budget constraint is represented as the price of good X multiplied by X, which is the quantity of X that is consumed, and the price of good Y multiplied by Y, which is the quantity of Y that is consumed. And this expenditure on good X plus expenditure on good Y should be equal to income, which is represented by I in this case. Now, a number of techniques can be used to solve this. The most popular approach is the Lagrange method, which involves the following steps. The first step is to write the Lagrangian function. This simply means writing the function to be maximized, which is our utility in this case, plus lambda times the constraint, which is our budget. So we will discuss what the interpretation of the variable lambda is in a few minutes. Then step 2 is to differentiate the Lagrangian expression with respect to x, y, and lambda and set the derivatives equal to 0. Keeping our Lagrangian function in mind, if we differentiate this function with respect to x, we are simply going to have differentiating first the utility with respect to x, which is going to be our marginal utility of x. So we showed in our previous lessons that anytime we differentiate a utility function with respect to x or to y, this simply gives us the marginal utility, which is how total utility changes as we change x or y. So the first function that we are going to differentiate here is the utility function, which is going to give us the marginal utility of x. And then the next thing we are going to differentiate is this entire equation here, which is going to give us minus lambda px, and we set this equal to 0. So we can rewrite this as marginal utility of x equals to lambda px. Let's call this equation 1. Then we move on to the differentiation of the Lagrangian function with respect to good y. Similarly, just like we had for x, we're going to have marginal utility of good y minus lambda py equal to 0. Now, this can be rewritten as marginal utility of y being equal to lambda py. Let's call this equation 2. Then the last thing we're going to do is differentiate our Lagrangian with respect to lambda. Now, if we recall our Lagrangian function, the lambda is multiplying the entire budget. Differentiating our Lagrangian function with respect to lambda is simply going to give us our budget. So let's write this here. So we have I minus px x minus py y being equal to 0. Now this can be rewritten as pxx plus py being equal to pi. Let's call this equation 3. So the next step in using the Lagrange method is simply to solve the system to find the utility maximizing bundle. So let's include some numerical values so that we can move on with our solution. Consider a consumer named Ella who has a utility function represented by this, and the price of good X as 6 and the price of good Y as 3 and income as 120. So with this information, let's follow the steps that we have shown above. So the first step is to write our Lagrangian function. So in writing our Lagrangian function, we know that we simply have write our utility function, which is the function that we are maximizing, plus lambda multiplied by the constraint, which is the budget constraint in our case. Then the next step is to differentiate this Lagrangian function with respect to x, y, and lambda, and then set the derivatives equal to 0. So if we differentiate the Lagrangian function with respect to x, we have 0.5 x minus 0.5, y 0.5 minus lambda 6, which is equal to 0. As we have shown above, this bit is a marginal utility of x, and this bit is simply the price of good x. So we can rewrite this as 0.5 x minus 0.5 y raised to the power 0.5 being equal to lambda 6. Now let's call this equation 4. Then the next thing is to differentiate the Lagrangian with respect to y. So if we differentiate our utility function first, we have 0.5 x 0.5 y minus 0.5, and then we have minus lambda 3, which is equal to 0. This again can be rewritten to be 0.5 x 0.5 y minus 0.5 being equal to lambda 3. So let's call this equation 5. And finally, we know that we have to differentiate our Lagrangian with respect to our lambda, which simply gives us the budget. So we have 120 minus 6x minus 3y being equal to 0. And this is the same as 6x plus 3y being equal to 120. Let's call this equation 6. Now, the next step is to solve this system of equation to get the optimal quantity of good x and good y. So let's keep these equations in mind. Equation 4, equation 5, and equation 6. So the first thing we are going to do here is to divide equation 4 by equation 5. So let's remember equation 4 is this and equation 5 is this. So we have 0.5 x minus 0.5 y raised to the power 0.5, which is equal to lambda 6, and we are dividing all of this by equation 5. So 0.5 x raised to the power 0.5, y raised to the power minus 0.5, and then we have lambda 3. So the two lambdas can go, 0.5 and 0.5 can also go. Now, in our previous lesson, we saw that the left-hand side, which is this, can be simplified into y over x, and this is equal to what is left here, which is 6 over 3. So if we look carefully, what we are showing here is this bit is our marginal rate of substitution, which we saw in our previous lesson, and this is equal to a ratio of the two prices, which is price of good x over price of good y, which is shown here. This is typically our equilibrium condition. Now we can rewrite this condition as y equals 2x. So let's keep this also in mind. Now, the final thing we are going to do then is to move forward to find our optimal quantity of x and y. So knowing that we can express y in terms of x this way, we have our equation 6 here. So instead of y, we are simply going to substitute the final equation that we have, which is y being equal to 2x. So let's rewrite this. We have our typical budget as 6x plus 3y being equal to 120. And we know y to be equal to 2x. So we have 6x plus 2x equals 120. So this is simply going to give us x being equal to 10. So now that we know x is equal to 10 and y is also equal to 2x, then we find y being equal to 2 multiplied by 10, which is 20. So in this example, the utility maximizing bundle consists of 10 units of good x and 20 units of good y. Now the next question is, what about lambda? In finding lambda, we have to remember our quantities of good x being equal to 10 and our quantities of good y being equal to 20. Now, if we substitute these two quantities into either equation 4 or 5, we are going to obtain lambda being equal to 0.118. Now, to see this, let's use equation 4. So equation 4 above is 0.5, x minus 0.5, y 0.5, which is equal to lambda 6. So we know what x is, we know what y is. Let's simplify lambda. So we have 0.5, and then we have 10 raised to the power minus 0.5, we have 20 raised to the power 0.5 being equal to lambda 6. So this function is simply going to give us lambda being equal to 0.118. Now, what does this tell us? The lambda is the marginal utility of income, which represents the additional utility that is generated by an extra £1 of income. So mathematically, what we are simply saying is lambda is du over di, which shows how the utility changes when income changes by £1. So this is all that we have on our lesson on the Lagrangian method for finding optimal bundles of consumption. The next lesson will be on deriving the optimal demand functions. If you enjoyed today's lesson, consider subscribing. Thank you.